In the last video, we talked about how data is moved between RAM and cache, and how we determine where data goes in cache and what data to replace when the cache is full. In this video, I want to talk about similar concepts lower down the memory hierarchy, including how data is laid out in RAM and what we do if RAM fills up and we have to move data further down to a hard drive. Here I have a sequence of memory accesses that were performed by a simple C program I wrote. This first address corresponds to the location of a stack variable, and the latter two addresses are accessing a chunk of memory that I mallocked. We see that all of these addresses are 12 hex digits long, but on my laptop where I was running this program, there are only 16 gigabytes of memory. And if we were to index 16 gigabytes of memory with an address for every byte, then we would only have 2 to the 36 addresses. And so 9 hex digits are sufficient to represent all of the memory locations available in the RAM of my computer, yet the addresses that my program is accessing are 48 bits or 12 hex digits long. So in fact, these addresses that my program is accessing aren't actually indices into the RAM. Rather, they are virtual addresses that get translated into locations in memory by joint effort of the operating system and the hardware. The advantage of this translation from a virtual address to a physical address is that the operating system can manage for each of the programs that are currently running which chunks out of the physical memory are allocated to different programs, but the code within the program doesn't need to know exactly where in memory its data lives, which means, for example, that the compiler can generate a stack address in advance without knowing where in the physical memory the program will actually be located when it's running. This means that we can have many different programs that are running at the same time and sharing the RAM as managed by the operating system. So when we run a program, the operating system decides what memory to allocate to that program, and if the program requests more memory, then the operating system can allocate additional memory to it. So for example, when you call malloc in a C program, this will often result in a request to the operating system to allocate an additional chunk of memory for your program. To keep track of all of this, with multiple programs sharing the RAM and requesting and releasing memory as they run, the operating system needs some data structures that keep track of what programs have been allocated which chunks of memory. The main way that the operating system does this is by storing a page table for each process. A process is an instance of a running program. We distinguish a program, which is your code, from a process, which is your code actively running, because we could have multiple copies of the same program running at the same time. A common example where this happens is a web browser like Google Chrome, which has a separate instance of the program running for each tab in the browser. So each of those instances of a program that is running is a process, and for every process, the operating system stores a page table that maps its virtual addresses to the memory that has actually been allocated. So the job of the page table is to store translations from virtual addresses to physical addresses. And just like we saw with moving data between RAM and cache, data is moved around in large chunks. The blocks that we moved between RAM and cache were typically measured in the dozens of bytes, whereas the chunks of memory that we think about in RAM are typically much larger, measured in the thousands of bytes. And we call the unit of memory in RAM a page. But just like with blocks in cache, a page of RAM is a chunk of consecutive memory addresses. So if our program has put data at this address, which is in the stack frame for main, then that address is part of a chunk of memory called a page. The most common size of a page is 2 to the 12 bytes. So if we have 2 to the 12 bytes on every page, then that means that there are 2 to the 12 consecutive addresses that all move together as a chunk when we allocate RAM. And so that means that the low order 12 bits of any given address are all on the same page. And so in hexadecimal, 12 bits corresponds to 3 hex digits. And so if we split up the address, like we did with the cache, into the low order bits that are an offset within the chunk, and the high order bits that tell us which chunk we're referring to, then the offset is the low order 12 bits, or the last 3 hex digits. And then, just like we stored the tag in the cache, we need to store in the page table the remaining bits of the address so that we can map the page number to the location in RAM where that page is stored. So in this case, the high order 36 bits of an address tell us which page that address is on, and then the low order 12 bits tell us where in the page is the data we're actually looking for. So then for each page of memory that is currently in use by the process, the operating system will need to decide where in RAM should that page go. And this is accomplished much like when we split up the cache into lines. We can split up RAM into frames where the size of each frame in the RAM is the same as the size of the pages of data that we are allocating for each process. So if we divide the RAM up into frames, where the size of a frame corresponds to the size of a page, then we are splitting the RAM up into chunks of 2 to the 12th bytes. "16 gigabytes corresponds to 2 to the 35 bytes. So if we break up RAM into 2 to the 12 byte chunks, then we will have 2 to the 35 over 2 to the 12 separate chunks. So the number of frames when we split up the RAM will be 2 to the 23rd. So that means we will need 23 bits in order to identify a frame. And so a frame number corresponds to all but the last 3 hex digits of a location in the physical memory. So if this page of the process's virtual address space is stored in this frame of the RAM, then the process's page table needs to map this page number to this frame number. So as a process accesses virtual addresses that are on different pages, the operating system will allocate frames of the RAM to hold those pages of the process's virtual address space. And the operating system will then need to store in the page table for that process the mapping of which page is in which frame of the RAM. But we want this table to facilitate quick lookups of, for a given page, where in RAM is that page stored. And so we need an efficient data structure for storing this mapping. If you've taken data structures, then you've probably seen lots of different options for data structures that can store this type of mapping. But the page table does this extremely efficiently by taking advantage of the fact that page numbers can be treated as integer indices and uses the page number as an index into a big array that is storing the physical memory locations for different pages. So when our program first uses the page 7FFEE84A9, the operating system will allocate a frame of memory to hold that page, and then the page table will be updated to hold the mapping for that page. So if it was placed at this frame number, then at index 7FEE84A9 in the page table, we will put the frame number for the location in physical memory where that page has been allocated. Then later, when the program accesses a different page, that page will be allocated somewhere in RAM. Then the frame of RAM where this page was placed will be recorded in the index of the page table corresponding to the page number from the program's virtual address. Then if we subsequently access some other address that's on the same page that we already allocated, there will be a mapping for that page in the page table. And so when our program tries to read or write data at this address, that address will be translated by the page table into the address that begins with these hex digits, and then to access within the page, we append the offset from the address that the program issued, which gives us a location in the physical memory, which frame and which bytes within that frame is the program trying to access. So this procedure of taking a virtual address requested by a process, looking up the page number in the page table, and then appending the offset from the virtual address to get a physical address in RAM is known as address translation. And this address translation is happening for every memory access that any process does. But there are lots of tricks that the operating system and the hardware can use to optimize this translation, including ways of shrinking the amount of space required to store the page table, and caching recently used translations in a special purpose portion of the cache within the CPU to avoid having to invoke the operating system's data structures every time we access data. If those details are of interest to you, our operating systems class goes into much greater depth on how address translation can be optimized. One additional component of the page table is a valid bit, much like we saw in the cache metadata. In this case, the job of the valid bit is to tell us whether a particular page of a process's virtual address space is currently in memory. So, for pages of the address space that the process has not accessed, those will have a valid bit of 0. And for pages that have been accessed recently and are therefore in the RAM, they will have a valid bit of 1. But the operating system, in managing the memory of many different running processes, might sometimes decide that a page of memory that a process is still in principle using hasn't been accessed in a long time, and in order to make memory available for a different process, might swap that page out of RAM and onto a slower and larger level of the memory hierarchy. In particular, it's common for an operating system to reserve some portion of the computer's hard drive for swap space. Swap space is a region on the disk that the operating system can move pages from the RAM that have not been used in a while if too much RAM has been allocated. This means that your computer can have lots of processes running that are in total taking up more memory than is actually available in the RAM, and some pages of some processes' address spaces will be swapped down the hierarchy onto the hard drive. And so it might be the case for certain pages that have not been accessed in a while that they will be swapped out to the disk and will have a valid bit of 0. And this means that the operating system needs to implement a page replacement policy, much like the hardware needed to implement a cache replacement policy. If the RAM is full, then the operating system will need to decide which pages of RAM can be sent to the hard drive and stored in swap space, and it therefore needs to predict which pages of RAM are less likely to be used in the near future, and keep the more likely to be used soon pages in the RAM so that they can be accessed more quickly. We therefore have an analogous concept to a cache hit or cache miss, which are known as a page hit or a page fault when we're talking about RAM. When a page fault happens, that is, when a process is looking for data at some virtual address, and we take the page number portion of that virtual address and look it up in the page table and find that that page is invalid, this is a page fault, and a page fault will invoke the operating system. So that means that the running process will have to pause for long enough that the operating system can start running, can figure out where is that page. Has it been previously allocated and swapped to disk, or is it instead not yet allocated and a new allocation for this process needs to be made in the RAM? Then once the operating system has either found or allocated the page that was invalid in the page table, it will mark that page as valid and return control to the process so that the process can proceed with using the data in that page of memory. We'll talk much more about the ways that the operating system manages processes soon. In summary, we've now seen that the hardware manages moving data between the RAM and the cache, and the operating system manages allocating data in the RAM and sometimes moving data out of the RAM and onto the disk. In both cases, we can split up the bits of an address into an offset that is within the chunk of data we're moving around, and a tag or a page number that lets us keep track of which chunks of data are stored where. So we have conceptually similar operations going on between different levels of the memory hierarchy. But the details of those operations differ in large part because of the relative speeds and sizes of the different levels of the hierarchy. When we're thinking about cache replacement, those policies have to be implemented entirely in hardware because cache accesses need to be incredibly fast. On the other hand, when we're talking about page replacement and where pages are allocated in the RAM, we are working with big enough chunks of memory that we're not going to be allocating pages all of the time. If, for example, the operating system allocates a page of memory to hold some of a process's function stack, not until the process has expanded its function stack to be bigger than 2 to the 12 bytes will the operating system need to allocate another page. So the chunks of data are much larger and the timescales are much longer when we're thinking about paging. So I hope that all of this is of some interest just in terms of finding out what's going on under the hood on your computer. But it's also worth asking, when is this important as a user or a programmer? Well, one case where this really affects the behavior that you'll get out of your computer is when you are using enough memory that things start needing to be sent into swap space. A common occurrence is that you've written a program that is hogging tons and tons of memory, and suddenly that program goes from processing data at a reasonable speed to slowing down by several orders of magnitude. And that tends to happen right at the transition when you go from having enough space in the RAM to store the data that you're working on to needing to store your data on the disk. And so if your program is using enough memory that it is bigger than the RAM available to it, it can often keep running, but when it starts accessing data, it will be accessing data that's not in memory some of the time, and those memory accesses will take orders of magnitude longer because the operating system needs to be invoked and data needs to be retrieved from the hard drive into RAM. And so to avoid that sort of slowdown, it's important to think about localities in your data and how can you do as much of the processing within a single page as possible so that your program doesn't end up going back and forth between pages that are in RAM and on the hard drive. Another case where these things become important in practice is if you have tons and tons of tabs open in a web browser, that can often take up huge amounts of memory on the computer because each tab needs its own page table and other resources for each process. And so if all of those tabs have chunks of memory assigned to them, eventually it will become the case that some of the memory for some of the tabs will need to be swapped out to the hard drive. And so if you switch to a tab you haven't used in a while, that can take a very long time because the pages of memory for that tab will need to be retrieved from swap space back into the RAM. So next time your laptop grinds to a halt, it's worth thinking about how much memory are my running processes using, and is the reason everything got so slow because we're having to retrieve data from the swap space.